Hi, welcome to Ordinary Differential Equations. Today we are going to continue our conversation about Laplace Transform. We started with the basic introduction last time, and today we are going to go and take a look at hyperbolic and circular trig functions. Let me just say a few words about hyperbolic trig functions. Some of you might not remember it from calculus. Well, we have two functions that look a little bit like the regular trig functions, but they have an extra h in them. Sine hyperbolic of t is exponential of t minus exponential of minus t over 2, and cosine hyperbolic of t is exponential of t plus exponential of minus t over 2. The second of these things is famous, and it's called the catenary curve. We are going to take a look at the Laplace transform of these things. The derivation of the transform is going to be very straightforward because last time we worked all the detail of Laplace transform of these ingredients. So this is going to be very quick. Next, we are going to take a look at Laplace transform of ordinary sine and cosine. That's going to be a little bit more elaborate because it doesn't have as easy and straight formula as in these cases. Before we go down to topic of Laplace transform, let me just make a plug for this particular function. Sometimes calculus classes skip the topic because there's so much other thing to learn. But cosine hyperbolic is actually a very famous function. Let's go ahead to take a look at several examples of these things. Let's see, what do I have here for you? It's called catenary because it's the shape of a hanging cable. So hanging cable you see here. The shape of this is according to that function, cosine hyperbolic of x or t. Here's another example. We can have the actual cable. So sometimes this is referred to as a cable function. A cable that is hanging between two poles will form the shape of the catenary. Here's another example, more pleasing to the eye. That is, of course, a cobweb. And you see the same thing so long as these beads are spread evenly. Catenary shows up in architecture quite a bit. This is a work of Gaudi in Spain, I believe. You see examples of his work in many of the buildings he built. These archways are based on that curve. Sometimes you see it in a modern architecture. And this is, of course, the gateway arc in Missouri. It's almost a catenary curve upside down. This is an example of a modern construction somewhere. And this is some bridge, again, based on that curve. This is a more elaborate one. And the shape of catenary looks very close to shape of a parabola. So sometimes people mix them up. We want to say that they are not actually same functions. They're actually quite different in their formulas and properties and such. And parabola has many uses too and shows up in shapes of certain type of bridges, but not to be confused with the shape of a catenary. So let me skip through these. For example, this is the Golden Gate Bridge, and the shape of this cable is closer to that of a parabola as opposed to catenary. And the reason for that is that this cable is supporting the road down here, and that road is perhaps equal weight per unit of length, and that forces the cable to take a shape of a parabola. So we have to be a little bit careful on that. You probably see much more detail in your engineering classes. Here is a nice demo of this curve. So you see several pieces of a chain, and they are all in the shape of that curve. And perhaps in your physics classes you'll do the derivation why is it that this has that particular shape to itself. This is again, these are examples of that catenary, and some other applications of it, rather out of the regular realm. This is a square that is turning on a catenary, and so on. So you can go and take a look at that and play with it. Another place where catenaries show in the special kind of soap bubbles. If you make two rings and form a soap bubble between the two rings, that's also in the shape of a catenary. So this is a homemade version of this thing, and you see that cosine hyperbolic showing here in description of this soap bubble. So we are just trying to say that this curve is not just a mathematical game, rather it's dictated to us by the natural world. The other one, sine hyperbolic, there's some far-fetched example of uses of it, but I didn't think it would be useful to bring that up here. Okay, after that long introduction, what's the Laplace transform of these curves? Let's see. Suppose I want to take Laplace transform of sine hyperbolic of, let's write bt, like for example 2t or 3t or something, some multiple of t. So that would be Laplace transform of exponential of, so instead of t I have bt minus bt over 2. And of course, by linearity, I can break this thing up as Laplace transform of exponential of bt minus 1/2 of Laplace transform of exponential of minus bt. Well, you remember last time we made Laplace transform formulas for exponential. So, for example, so what was the formula we had last time? We said Laplace transform of exponential of a certain multiple of t. We derived the formula was 1 over s minus a. Is that right? So I can continue. For this one, it's going to be 1/2 of, I have a factor of 1/2 times 1 over s minus b, and then minus 1/2 of 1 over, this is minus b, so s minus b. So I can factor my 1/2, so I'll have 1 over s minus b and minus 1 over s plus b. This is good, but perhaps we can clean it up by taking a common denominator, product of these two, s minus b, s plus b, cross product, so 1 times s plus b, and then minus 1 times s minus b. So 1/2 of, in the numerator, s's cancel, I have 2b. Denominator, if you multiply it through, is s squared minus b squared. 2's you can cancel. B over s squared minus b squared. So we have the following one, Laplace transform of sine hyperbolic of bt is b over s squared minus b squared. Let's write an example. Laplace transform of sine hyperbolic of, say, 3t. So that's simply 3 over s squared minus 3 squared, which is 9. While we are doing any of these, we might as well practice the inverse as well. What's a Laplace transform inverse of 3 over s squared minus 9? Of course, if that's your output, that must be your input, sine hyperbolic of 3t. Typically, we come across situations where this number is not conveniently square root of this number, rather something else. So suppose I have 7 over s squared minus 9. How do you clean this up. So yeah, easiest way is to write multiplication and division. So I put a 7 outside, multiply by 3 and then divide by 3, so the 3 when 3's cancels, I still have my 7 over s squared minus 9. Now we use the linearity of Laplace transform. A factor of Laplace transform transfers to a factor of the original function, so 7/3 of sine hyperbolic of 3t. So if you want to make a more general formula for that, if you have like Laplace inverse transfer of a over s squared minus b squared, I do the same thing. I multiply and divide by a b here, and I'll get a over b of sine hyperbolic of bt. Okay, we talked a lot about sine hyperbolic. Let's go ahead and do example of a cosine hyperbolic of bt. What is the Laplace transform of it? So it's going to be Laplace transform of e to power of bt plus e to power of minus bt over 2. We just did this. The only difference with the previous arrangement was that that was minus and this is a plus. So I'll have 1/2 of 1 over s minus b for the first one, plus 1 over s plus b for the second one. And when we simplify the sum, I get 2 s's divided by 2, and that becomes s. And I multiply the denominator, becomes s squared minus b squared. So let's write this thing separately. Cosine hyperbolic of bt. What we found out was s over s squared minus b squared. You might want to go through the details of this thing yourself second time, but it's exactly like what we did. An example, Laplace of cosine hyperbolic of 70. Yeah, that's going to be s over s squared minus 7 squared. And similarly, if I have inverse Laplace transform of s over s squared minus 16, I can quickly say that must have been cosine hyperbolic of, what is that now? This is of course the multiple here is square root of this one, so it's going to be 4t and so on. Okay, so that's for the cosine hyperbolic. Okay, now we want to go after sine, regular sine and cosine. So to distinguish between these two groups, the one with the h is called hyperbolic, the other one is circular, because these are based on the shape of a circle. That one is based on the shape of a hyperbola, and the formulas look very similar to each other, but in some sense they are a word apart because these functions are so different. Let me just go ahead and write one of these, or both of them, and then we go after finding, explaining where they come from. Laplace transform of sine of bt. So this is going to be the ordinary sine. The only difference between this and the problem that we had where did we have this? Here. The only difference between the two formulas at the end would be instead of a subtraction, we are going to have an addition. The two functions are extremely different, but at the end, that's all that happens. So this one turns out to be b over s squared plus b squared, and for the cosine, what do you think that's going to be? So it's going to be similar to this, and again the difference is that the denominator is the sum of these two. Remember, if you have difference of two squares, you can factor it, and if you have a sum of two squares, well, it's entirely different. Either you say it cannot be factored, or you say if you want to factor it, you need complex numbers. Now, derivation of these two formulas, there are quite a few different ways of approaching them. Any textbook that you study is going to have at least one method of doing this, and perhaps some other methods are delegated to the exercises. So you can more than likely see that you can obtain the formula by repeated integration by parts. That's one style of doing it. So I'm going to let you study that in your textbook. And I'm going to go ahead and use one of the Euler formulas so that we can do this thing in a slightly different way and also become familiar with the Euler formula. So remember, Euler formula was saying that exponential can be written as exponential of an imaginary number can be written in terms of sine and cosine. Why is this a natural choice here? Because sine and cosine can be expressed in terms of exponential, and then this exponential I can use it in the context of the formulas I had before with the cosine hyperbolic or with the formulas we had developed before. We are going to take a little bit for granted in the sense that well, we haven't talked about complex numbers all that much, but we are going to take this thing with a bit of grain of salt with our derivations. So let's go ahead, do cosine of exponential of minus I theta will be cosine of minus theta, which is same as cosine of theta, plus I sine of minus theta, and that minus comes out, and the formula turns out to look like this. Okay, what does this give me? Suppose I want to capture cosine. So if I add these two, sines cancel out, and I get cosine of theta is e to power of I theta plus e to power of minus I theta divided by 2, which is based on the discussion that we just had. This is cosine hyperbolic of I theta. So there is a connection between trig function and their hyperbolic cousins at the expense of turning your input to its imaginary. We can connect these two functions. Same way with sine. Sine of theta, I can subtract these two. Cosine will cancel. I will have 2i sine theta. When I divide by 2i, I get what I want. So it becomes ei theta minus e minus I theta divided by 2. And then I will have a factor of I as well. So I'll see that this is 1 over I of sine hyperbolic of I theta. Okay, so a little bit of practice with complex numbers is going to help us. You're going to use these complex numbers in theory of circuits and much more advanced stuff. So instead of doing another example of integration by parts, I chose to do this one first. Next, let's remember the claim to fame of I. What is I? I squared is of course minus 1. So that's a crucial thing to remember when you're doing arithmetic with complex numbers. Now, the question was, what is Laplace transform of sine of bt? Okay, so let's go ahead and write what is sine of bt anyway. Sine of bt, suppose I want to write it in our new notation. That's going to be 1 over I of sine hyperbolic of, instead of, if you have a bt here, it will be ibt here, ibt. So Laplace transform of sine of bt, after that we want to establish this formula. I can say, well, Laplace transform of sine hyperbolic of ibt, but divided by I. Well, what was the formula for the sine hyperbolic? Let's remind ourselves. Formula for sine hyperbolic of bt was b over s squared minus b squared. Whatever the multiple is, shows up here, and square of it shows up here. So let's go ahead and do that. So this is going to be whatever the multiple is shows up in the numerator, and then s squared minus ib squared shows up in the denominator, and then we have a factor of 1 over I. Okay, let's go ahead and clean this up. So of course i's cancel, and ib squared would be I squared b squared. I squared is minus 1, and that minus cancels this other minus, and this whole thing boils down to just b over s squared plus b squared. Okay, the i's cancel. I squared became minus, and cancel this minus into a plus, and that's what we got, and that's what we intended to show anyway. So we have that. Similarly for cosine. For cosine of bt, I can replace it by cosine of bt. I can replace it by cosine hyperbolic of ibt. So Laplace of cosine of bt, I might as well take Laplace of cosine hyperbolic of ibt. And that was what? The multiple, excuse me, s cosine, for cosine, we had the following formula: cosine hyperbolic of bt, s over s squared minus that number squared. So s over s squared minus the multiple of t. Multiple of t is ib, and when you square it, I becomes minus 1, cancels this minus, makes it plus, so I'll have s squared plus b squared, and then s in the numerator. Okay, every now and then it's a good idea to take a stock of what we have established so far and practice the Laplace transform. So we have a table for specific functions. So I have, let's list the original function here, and its Laplace transform here. This is f of t, this is f of s, and we make a table just like we made them for either derivatives or integrals and such. So Laplace transform of 1 was 1 over s. You remember all of these came with a restriction, even though most often we put it aside, but they do come with a restriction. So next we had exponential of a multiple of t, and that was 1 over s minus a, and here s had to be larger than a. And then we had t, or t to power of n. T to power of n was n factorial over s to power of n plus 1, and here again s is positive. Next we had cosine hyperbolic of bt, and that was s over s squared minus b squared, and then sine hyperbolic of bt we just found today, and that one was b over s squared minus b squared. In these cases, s has to be larger than both plus and minus b, so we can write it at s larger than the absolute value of b. Two more formulas we found today: cosine of bt, and that is just s over s squared plus b squared, and then we have, of course, sine of bt, and that's just b over s squared plus b squared. Let me correct this. This is b squared. For these two, for sine and cosine, it turns out all we need is for s to be positive. B doesn't play any role in our discussion. Now, okay, so this is our temporary table. It has what? 1, 2, 3, 4, 5, 6, 7 formulas. Of general formulas, we have a set of general formulas here. Of course, we have, if you have a function f of t, we have our definition of what this whole thing is about. If we don't find our f in our table, then we have to go back and do it the hard way, or create the formula from scratch. So this is our definition for what this is. That is for Laplace transform. Simplest formula that we have here is that if you have a constant times a function and another constant times some other function, and these two have Laplace transforms, then their Laplace transform of the sum or difference is just made from the same combination of f and g. So for example, you have an exponential and a polynomial, and they are added to each other. You take a Laplace transform of each of them, and then you simply add up their Laplace transforms. As rules go, that's pretty much the only easy one here. After that, everything else is going to become more complicated. If you have some product of the two functions or division of two functions and such, we cannot go ahead and take the Laplace transforms of the individual components and say multiply them or divide them. So for example, if you have exponential times polynomial, this times that, we can't simply just go ahead and multiply this one with that one. We are going to see that for some cases we have some special formulas, and they are rather intricate, but it's never as simple as just multiply the pieces. You actually did not have such a rule for differentiation or integration either. So the only rule that is across the board easily applicable to all cases is a linear combination. Beyond that, we have to build everything from scratch. As a side note, we noticed that mathematically speaking, this factorial here is very interesting. It gives you a way of describing what is the factorial of fractional numbers. If you are interested in that, you want to read your textbook or any book about so-called gamma function. Okay, as I said, if you have a function that doesn't easily fit in your table, then you're facing the task of creating your answer from scratch. Some of these we might do now, and later on go ahead and actually make a machinery for doing it based on a table. So of particular interest in engineering, an application of Laplace transform is how to handle discontinuous functions. When you take your calculus and pre-calculus and such, pretty much all functions are continuous. You rarely come across discontinuous functions. But in engineering, quite ordinary to have discontinuous functions. Pretty much every device you deal with has a discontinuity in it, and discontinuity comes in with some button on the device that you can, for example, turn it on and off. Or if you have, say, a washing machine, it has all these cycles. It goes from one mode to another mode to another mode, and these are discontinuously changing what the machine is doing. So discontinuous functions are quite common in engineering, and to answer problems from engineering, they need to handle those discontinuities. Now, the way we deal with discontinuities in mathematics is by the so-called piecewise defined functions. So you see like a curly bracket, and you see a list of formulas here. For example, let's keep this thing a simple one. Suppose it says function f of t is -1, and sometimes it is 1. When is it -1? Then we describe when that happens. For example, we say when t is between 0 and 1, then the output of the function is -1. And if t is larger than 1, then the output of the function is 1. Again, this type of functions are seen in practice as often as you see it in mathematics. So it might come at you as looking like a weird function, but actually every time you go to a post office, you see a discontinuous function for pricing. For example, it tells you if the weight is up to so many ounces, it's certain price, and then above a certain weight limit, it's some other price, and they have a whole table here. If you deal with credit card companies, if you deal with ordering in pizza shops, all of these things, they give you, sometimes they give you volume pricing and so on. So depending on what you order and how big that volume is, the price per unit could be different. So discontinuous functions are very, very common in practice. And since Laplace transform is to be applied to practical situation, we need to have a machinery for dealing with discontinuous functions. So for example, this could be a force on some spring, and we want to handle how that spring is going to react to the force and so on. So here we are taking the problem from step 0. How do you calculate Laplace transform of some function that is not in your table? Like, I don't see anything resembling this in my table here. There is no, these are all polynomials, sine and cosine. Nothing looks like a discontinuous function of this type. Well, then we have to go back to the original definition. It's an integral of whatever you have times something that we call the kernel. Then we integrate. Okay, next problem is that we don't have a straightforward formula here to put here. We have a function that breaks. The easiest thing is to take this domain of the integration and break it according to the limits that you have here. That is, I go ahead from 0, instead of going straight from 0 to infinity, I go from 0 to 1, 0 to 1 of f of t exponential of minus sdtt, plus then from 1 to, was t larger than 1 means go all the way to infinity, from 1 to infinity of f of t exponential of minus st dt. Taking a function, the integral, and breaking it into different pieces of its domain, the standard thing that you do in calculus 1. Now we say, well, from 0 to 1, my function is defined a certain way, so I put that definition here, so it's -1. I put that, and then I put the other one. So from 1 to infinity is 1. Of course, we don't need to write 1, but I'm just indicating that that's where it came from. Now the way we are approaching this, we are doing everything from scratch all over again. So we have to do the integrals. Antiderivative of exponential of minus st. Well, that's easy enough. Divided by minus s, and I have a factor of minus 1 here. And then I have limits from 0 to 1. Plus this one, the factor is 1. And the derivative is just like what we did. And that one, the limits go from 1 to infinity. Okay, at 1, this becomes minus exponential of minus s. At 0, exponential of 0 is 1. I have to subtract it, so I get plus 1 over minus s. How about here? Exponential of minus infinity times minus s times infinity. If s is positive, this approaches 0. So let me write, I have a factor of 1, exponential of minus s times infinity, and then I'm putting 1 there, exponential of minus s times 1, the whole thing divided by minus s. Now, just what we said in the first lecture, if you take s to be positive, that this collapses to 0. If you take s 0 or negative, you are going to be dealing with infinity. So to keep it simple, s is positive for this to go away. And I'll go ahead and simplify exponential of minus s plus 1 over minus s, and this one I have minus exponential of minus s over minus s again, and it all boils down to 1 minus 2 exponential of minus s over minus s. It's customary not to leave a negative in the denominator, so it might be written as 2 exponential of minus s minus 1 over s. Okay, so what we learned here is that if the function we are dealing with is not in our table at this point, we simply go ahead to the drawing board, start calculating from scratch, which means taking our function and integrating. If the function is discontinuous, then we break the integral, or if the function is piecewise defined, we break the integral according to the breakdown of the t's, and then we are gonna be done. So another important thing is that we had this preliminary table, and we learned something about sine and cosine hyperbolic and the catenary curve. Until next time, good luck and God bless.